Okay, we're continuing with Chapter 11. We're talking about different methods for determining if a series is convergent or divergent. We've talked about the integral test, the comparison tests. Now we're going to talk about tests for alternating series in section 11.5. Okay, and so this, as the title of the section suggests, we're not using alternating series to test some other series or something like that. This is, if we have an alternating series, how can we test that alternating series to see if it's convergent or divergent? That's what this section is about. So the convergence tests that we have looked at so far apply only to series with positive terms. Yeah, exactly. So this statement here, one thing to note is that so far the integral test and the comparison tests were strictly applied to positive series or sequences turned into series where the sequences have only positive terms. But you can think about, though, let's say you had a series with only negative terms. Well, then those still apply. You can still test those using the methods we've talked about so far, because you could just take the negative sign out and put it in front of the sum and then run the tests. Okay, so in that sense, we have covered series that have all positive or all negative terms, at least for a portion of the series, that a starting point n is equal to whatever all the way to infinity. That's the case. Now you could have series with both positive and negative terms. In one case, that would be an alternating series. That's what we're going to talk about here. But another case could be, it's not alternating, but something like cosine or sine over like n squared. So that would, do like that all the way to infinity. Well, that's not alternating, right? But that has positive and negative terms. And so how we deal with a series like that, we'll talk about in the next section. But, I want to note, though, so it is important that, we're saying that it's always positive or always negative, and it doesn't have to be for the entire range of the series. It could be just from some n is equal to whatever to infinity, because, you might think that always being positive or always being negative is constricting, that really limits the amount of series you can test, but not really. So yeah, like around the origin, or like within plus or minus, a finite value of the origin, you got all kinds of stuff going on, right? Could be crossing the x-axis. But when you're going off to infinity, you don't have, most of the time, you're not going to have much, you're not going to have much behavior going on with the function. It's always going to kind of settle out to something, right? You don't go out to with a function, you don't go out to a million or whatever, and you have all kind of stuff going on usually. So what I'm saying is since you can test a series for convergence by starting at any n you want, like at n is equal to 50 or whatever, then that really, you're going to end up with a lot of series are going to behave that way, where they're always positive or always negative going off to infinity. Okay, in this section and the next, we learn how to deal with series whose terms are not necessarily positive. Of particular importance are alternating series whose terms alternate in sign. So again, why is this not an alternating series? Like cosine of n over n squared. Well, with an alternating series, each term is alternating positive and negative. Like you could have, this could be n is equal to 2. Or no, this could be n is equal to 10. This could be n is equal to 11. This could be n is equal to 12. And then this is n is equal to 13. It's not alternating sign each term. An alternating series is distinctive. It has this, a minus 1 to the n, or a minus 1 to the n minus 1. It's every single term, it alternates in sign. You don't have with a cosine of n over n squared, you don't have a term like this, right? So an alternating series, the terms alternate in sign. An alternating series is a series whose terms are alternately positive and negative. Here are two examples, right? Each term is changing sign. You can turn any of the series that we've talked about so far, you could turn it into an alternating series by just putting a -1 to the n minus 1 or -1 to the n, depending on, here the first term would be positive and it would alternate from there. Here the first term would be negative and it would alternate from there. And so this is 1 over n as an alternating series. This is n over n plus 1 as an alternating series. We see from these examples that the nth term of an alternating series is of the form. Yeah, so any alternating series, you could separate out the positive portion from the negative portion, the alternating negative portion. Now, this is a little confusing because you might wonder, well, okay, so if I had this series, right, and so cosine of n over n squared is, again, it's going to do like that and decay all the way to 0. You might wonder, okay, well, what if I did this? What if I had this series? So yeah, this is an alternating series, right? It's got this -1 to the n. No, this isn't going to be an alternating series, because what's going to happen is you're going to, like, okay, for some portions it'll behave like an alternating series, but in general, overall, it's not an alternating series because, like, okay, when we get around here, we might have something like when we get to a crossover point, we might have, okay, that's n is equal to 5, let's say, or I don't know, or n is equal to 20. That's n is equal to 20. And that has a, right, like, okay, so you're like, this is n is equal to 18, 19, 20, that's 21. So, okay, we're always positive here. Cosine of n over n squared is always positive. So, yeah, we're alternating, right? Let's say we go, the -1 to the n is negative here, so we have a negative number. Then we switch to a positive number. Then we switch to a negative number. Then we switch to a positive number. But then we get to, this would be n of 22. Okay? So, okay, we went, what was it? Negative, positive, negative, positive. And then cosine of n over n squared becomes negative, but this is negative. So we go positive, positive. And then we go back to alternating, right? So it's like alternating, and then you have two successive terms that are the same sign, right? So technically, that's not an alternating series. You created a series that's alternating in character here, but it's not by definition an alternating series. Okay, these tests here are for a true alternating series. Every other term changes sign. That has to be the case for to apply this test. And so if that, with cosine of n over n squared, with cosine of n over n squared with a -1 to the n minus 1 or -1 to the n out front, you couldn't do this. You couldn't separate out a positive term from the -1 to the n or nth power term, right? They're saying b sub n is the absolute value of a sub n, right? You cannot write -1, you can't write -1 to the n power cosine of n over n squared like this. Separate out some b sub n that's always positive from this term. Okay, but so a true alternating series, you can do this. You can write it this way, right? So b sub n is equal to the absolute value of a sub n is what this means. Okay, the following test says that if the terms of an alternating series decrease towards 0 in absolute value, then the series converges. Okay, so again, what is this saying? The following test says that if the terms of an alternating series decrease towards 0 in absolute value, then the series converges. So this is, what they're saying here is that with this test, we can go straight to the sequence. We take the absolute value of the alternating series, which is b sub n, and we analyze the limit of the sequence b sub n. If that equals 0, the series converges. Remember, we couldn't do this before. We can't do this with any series. We can't take the limit of the sequence, and if that limit equals 0, make a conclusion about the corresponding series. we can make a conclusion if the limit of the test for divergence, if the limit of the sequence is not equal to 0 or it diverges, we can say the corresponding series diverges. But if it equals 0, we can't make a conclusion about the series. For an alternating series, however, we can do this. Now, but we take the absolute value of the alternating series, which is the b sub n here, and we analyze the limit of that sequence. If the limit of that sequence equals 0, then the series converges. Now, there is one caveat to that, in that the b sub n needs to be monotonic decreasing. So it needs to be like, the b sub n, every b sub n plus 1 needs to be less than or equal to b sub n for all n, or, you can start at n is equal to whatever. This needs to be the case for n starting at n is equal to whatever, right? So that has to be the case, right? And you can have a positive b sub n that doesn't necessarily, it's not decreasing like that. So that's the caveat, that it needs to be decreasing. Okay, so it says before giving the proof, let's look at figure 1, which gives a picture of the idea behind the proof. So yeah, they give a kind of a description of an intuitive description of why this theorem works. We first plot S sub 1 is equal to B sub 1 on a number line. So we're at 0 here, and so here's S sub 1, and that's B sub 1. To find S sub 2, we subtract B sub 2. So S sub 2 is to the left of S sub 1, right? So we're looking at these B's are positive, but now we're thinking about subtracting B sub 2, because that's what you would do with the alternating series, right? So B sub 1, and you subtract B sub 2, you get to S sub 2, but we know since B sub 2 is less than B sub 1, based on the requirement, we're not going to go past the start point. We're not going to go past the 0 point. We're going to come to like here. Then to find S sub 3, we add B sub 3. Okay, but we're not going to get back to this S sub 1 point, because again, B sub 3 is smaller than B sub 2. And it's that same idea. You keep doing that. You're never, because the terms are decreasing. You're shrinking down to this point S that you converge at, right? Because it's alternating. Every other term alternates, so you're subtracting. That's the thing, and you can get a sense for why with like cosine of n over n squared. This proof, you can't use this proof, because you have these terms mixed in where you're adding two terms or subtracting two terms, and that could potentially mess it up. You have to do a whole nother proof. But yeah, so you keep doing this, and as you go to infinity, you converge to this S here. Okay, so they give the proof here. Now, okay. Here's the alternating harmonic series. So the harmonic series, but alternating, right? So we've taken the harmonic series and turned it into an alternating series by just putting a -1 to the n minus 1 on it. Yeah, and so you can imagine you can't just turn any series into an alternating series by just adding a -1 like this to it, because it's like it can't, unless it's always positive or always negative. Then you can do this. But like, again, cosine of n over n squared isn't always positive or always negative. So it doesn't mean you can't necessarily turn it into something like an alternating series. You just have to, it's not as simple as just adding a -1 to the n or -1 to the n minus 1 to it. Okay, but we know that harmonic series is divergent by itself. So what about the harmonic series as an alternating series? Well, okay. B sub n plus 1 is less than B sub n. It's decreasing. 1 over n is decreasing, right? This is the absolute value, so we're just thinking about 1 over n. Okay, now the limit as n approaches infinity of B sub n is equal to 0, so that's it. That's simple. This series is convergent. Okay, here, this series is alternating, okay, so is it decreasing the absolute value? Yes, and it's always positive. But the limit is equal to 3/4. So 3/4 is not equal to 0. So this is going to be, it's an alternating series. And so it's going to be divergent. But we can actually prove that with the test of divergence, right? Because if any alternating series, it doesn't tell us here, if we come back, It's not like it states explicitly that it's that what makes it divergent, but if you have an alternating series that satisfies this condition and that means it's convergent 100%, well, then if it doesn't satisfy this condition, then that must mean it's divergent, right? But they can prove it with the test for divergence by just taking the limit of the actual a sub n. And so this limit goes to 3/4, but with the -1 to the n power, you're oscillating from plus or minus 3/4 all the way to infinity. That's diverging. So this is, like with the test for divergence, we actually take the limit of the actual sequence. So the limit of the actual sequence is you're going plus or minus 3/4 all the way to infinity. That's diverging. Okay, here's another alternating sequence. The given series is alternating, so we try to verify the conditions of 1 and 2 of the alternating series test. But here it's not obvious if this is decreasing. I mean, I think you could, with n cubed, you could make a guess that it is, but if you want to get an official answer, you can they create an f of x and there's no issue there by replacing n with a continuous variable. Take the derivative, and you see that this is decreasing when x is greater than the cube root of 2, but that's not an issue. It doesn't have, you don't have to start at n is equal to 1 to satisfy the conditions of these tests. We've talked about this many times. So this is, going off to infinity, the derivative is negative, so this is a decreasing sequence. So they take the absolute value, the b sub n, take the limit, it's equal to 0, so this series is convergent by the alternating series test. All right, so now let's talk about estimating the size of r sub n. Remember, each series convergence divergence test method comes with its own way of estimating the size of r sub n. Okay, and so also remember that when it comes to r sub n estimates, the idea is you've already determined that the series is convergent. There's no estimating the size of r sub n if the series is divergent. So we have a convergent alternating series. A partial sum S sub n of any convergent series can be used as an approximation to the total sum S, but this is not of much use unless we can estimate the accuracy of the approximation. I think I disagree with that statement a little bit. I think what we've seen is that if you go into a computer program and if you input n is equal to 500, it's probably going to be very accurate. But with a computer, you could do 5 million, and you could make an assumption that it's pretty accurate. I guess technically you'd like to know for sure how accurate it is, but still, I'm just saying. We worked example problems where summing the first 10 terms gets you like within 0.2% accuracy. Imagine using a computer to sum the first 5 million terms. Now, every series is different. I'm not saying, you could have a series that it takes a lot of terms to get to 0.2% accuracy, but I'm just saying, they say not of much use, almost like it's useless if you don't have an estimation for the size of r sub n. I would say I'm not sure if I'd go that far. The error involved in using S is approximately equal to S sub n is the remainder R sub n. So you should already know what R sub n is at this point. The next theorem says that for series that satisfy, real quick, that we're saying S is approximately equal to S sub n. We can't say the S is the infinite sum. Well, if the series isn't convergent, there is no S, right? So again, we're assuming the series is convergent. The next theorem says that for series that satisfy the conditions of the alternating series test, the size of the error is smaller than b sub n plus 1, which is the absolute value of the first neglected term. So yeah, this actually ends up being really simple. Now, okay, well, let's go through this theorem. So the alternating series estimation theorem, we've got this infinite sum, because it's a convergent series of this alternating series here, is equal to S, it's convergent. B sub n is greater than 0, yep, is the sum of an alternating series that satisfies. So yeah, if this is the case, if you have an alternating series to where the sum of the alternating series satisfies the conditions of the alternating series test, that it's decreasing, at least the absolute value of it is decreasing, and then the limit of the B sub n sequence is equal to 0, then the absolute value of the R sub n is equal to the absolute value of S minus S sub n. That's the definition of R sub n. Okay, but how big is this R sub n? It's less than or equal to B sub n plus 1. Okay, well, first of all, notice that it's saying this estimation of the size of R sub n here is strictly for an alternating series that you can put through this alternating series test that we've talked about in this section. And so meaning that, like, it's not like this, what we just talked about in this section applies to any alternating series, right? It's specific alternating series. They happen to have the condition that the absolute value of the alternating series of that sequence, that B sub n sequence, is decreasing for all n, or, for some starting n to infinity. You could have an alternating series that's not the case, right? I mean, it's like take any positive series that's always positive, but it's not decreasing, and put a minus 1 to the n in front of it. Now, I can't think of a series like that off the top of my head. I mean, to me, that would be like we talked about earlier in the video, that would be pretty rare, because you don't have a lot of activity going on with a function as you go off to infinity. It's usually pretty, it's going just constantly decreasing or constantly increasing, right? But still, just trying to be as thorough as possible here. Technically, that it has to satisfy this criteria to where you could test it with the alternating series test. Okay, so if it can be, if this is the case, it's decreasing, the B sub n is decreasing, and then if this is the case, then this has to be the case for it to be convergent. Then the size of the remainder is going to be less than B sub n plus 1. Remember, B sub n plus 1 is like when we talked about the meaning of the remainder. You've got the S sub n that you made the estimation with, and then all the other terms, so that the S sub n goes from like A sub 1 to A sub n, but then the full sum includes the A sub n plus 1, A sub n plus 2, A sub n plus 3. Well, they're just using the B here sequence because they're referring to you take this from the B sub n sequence. So this B sub n plus 1 will never be negative, right? This is coming from the absolute value sequence, right? So make sure you're understanding this. You've got the the infinite sum of the actual alternating sequence, the one we're analyzing, A sub 1 plus A sub 2 plus A sub 3 plus A sub n. That's like a partial sum, then plus A sub n plus 1 plus A sub n plus 2, right? And then the idea is you take S minus S sub n, and you're left with the R sub n. Here they're saying to estimate the size of the R sub n, you use the B sub n sequence. So the absolute value sequence. And you think about that in terms of its own, it has its own R sub n and S sub n. And so you take B sub n plus 1. Now, what is B sub n plus 1 going to be? It's going to be the absolute value of A sub n plus 1. A sub n plus 1 could be positive or negative depending on what order, what the minus 1 to the n or minus 1 to the n minus 1. But B sub n plus 1 is just the absolute value of A sub n plus 1. Okay, so the absolute value of the R sub n, and they say absolute value because R sub n could be positive or negative, right? It's this alternating sequence. You're adding, subtracting. Depending on the n, R sub n could be positive or negative. The infinite sum could be positive or negative. S sub n could be positive or negative. So they're just saying the size of the R sub n here is going to be less than or equal to B sub n plus 1. Okay, so but in general, though, you can see this is really simple. Okay, so they give the proof here. Now let's take a look at this example. Find the sum of this series correct to 3 decimal places. So they first make sure it's convergent, and they do that by, so they just take another, you can say from, I'm not sure what I think they just 1 to the n plus 1 over n plus 1 factorial. If you show that that is convergent, then then 1 over n factorial is convergent because it's the same series. You could just change the start point, right? 1 over n plus 1 factorial, if that's not convergent, if this is a decrease, if this is decreasing, each of these successive terms is decreasing, then definitely 1 over n factorial is going to have successive terms be decreasing, right? And they do this because we can say that, turn this into 1 over n factorial times n plus 1 is less than 1 over n factorial. But couldn't we have done that with, we could have said 1 over n times n minus 1 factorial? I'm not sure, but they prove that this is decreasing in this step. That each of the terms of this b sub n, the absolute value of this is decreasing. And then here, they take the limit of the b sub n sequence and show that that goes to 0. So they prove it's convergent. So then next what they do is they write out a few terms of the series, the actual series, not the b sub n series, the a sub n series. Okay, they write out some of the terms, and so what they're doing here is they're saying that so they want it correct to 3 decimal places, and so you can just look at this and say, you can look at this list here and say, okay, if I did an approximation as it would be s of 1, 2, 3, 4, 5, 6, s of 6, then that would be accurate to within this 1 over 7, 20. If you did 1, 2, 3, 4, 5, 6, 7, s of 7, that's going to be accurate to within the absolute value of this, which is 1 over 5,040. Okay, and so that is better than 3 decimal places. So then you add up the first 6 terms. So, okay, so here's s of 6. And they get this decimal here. Now, this is a little different. Up to this point, with series that are always positive, we've known that whatever s of n we calculate is always less than s, no matter what, right? That was always the case. Well, here it's not. It doesn't really work that way because we don't necessarily know that this is less than s because it's that alternating. It's subtracting and adding. We just know that this is within within 3 decimals of s because this doesn't affect the 3rd decimal place. Okay, so it says here the rule. Yeah, this is only valid for alternating series that satisfy the conditions of the alternating series estimation theorem, right? This isn't just universal for any alternating series.